data loss is perhaps the one key thing that we want to prevent from happening in our network. So I'm not sure if you know this or not, but probably not the most recent, but the attack on Target was because their video surveillance systems were on the same VLAN and IP architecture as their point of sale terminals. Even though their point of sale terminals were not hacked, what was effectively done was an escalation attack. Once the hackers got into the video surveillance systems, were able to leverage that attack and do an escalation attack inside the point of sale systems, and that's how all those credit card numbers, et cetera, got filtered out of their data centers. In addition, we have email security appliances, and email security appliances effectively secure our inbox and also protect us against things like spam and advanced malware, phishing, and data loss. And they also secure outgoing mail with policies that prevent data attachment. So where an email security appliance is actually used, which is an appliance-based apparatus that is only for email security, would be a good example of that would be in our medical environment. So if you're managing the security parameters of a medical environment, of course you're falling under HIPAA requirements, and you have to prevent medical records from actually leaving or going places that they're not supposed to go. Web security appliances also is an appliance-based apparatus that protects our web traffic. Oftentimes, we will proxy all of our, in an enterprise environment, we will actually proxy all of our web connections through a web security appliance. And web security appliances use, among other things, what's called dynamic vectoring and streaming engines, which is a way of having multiple anti-malware scanning engines combined with third-party verdict engines that basically say yes or no, we don't want to allow traffic to go here. And then, of course, web-based reputation filtering is a way of, again, in our ecosystem, systematically grading the safety and the non-intrusiveness of websites out on the internet, of which there are thousands. Now, we can accomplish all of this, right? So, for example, if our ecosystem just has the Cisco Next Generation Firewall, now we implement things like snort engines and snort rules. And also within the context of next generation firewalls, we have URL filtering, we have data exfiltration mechanisms that we can put in place that actually look at documents both entering and leaving the protected environment. And we can accomplish all of that from a common sort of place in the network. In addition to protecting our inbound and outbound traffic flows, we also want to protect our networks and our ecosystems from denial of service and distributed denial of service. Now, effectively, the difference here is that in a denial of service attack is usually from a singular bot, right, attempting to attack our network. Whereas a distributed denial of service attack looks more like multiple bots out here trying to affect a resource. So some of the solutions to prevent this from actually happening are things like stateful devices, so things like our firewalls and our IPS systems, et cetera, and also host-based intrusion prevention systems and firewalls. Connection limits, which would be things like, usually those are placed on the inside of the network to prevent attacks from occurring on the inside of the network, usually unintentionally. We can also use access control lists for things like traffic filtering based, again, on a set of rules. And then, of course, manual responses. Now, manual responses are usually done after an attack has occurred, and we're actually tuning our firewall. Now, I didn't say this earlier, but let me go ahead and back up to this. DOS and DDoS attacks typically look like traffic appearing legitimate as defined by the protocol. So, for example, 802.3 and 802.11 packets appear legitimate as defined by a protocol. DOS and DDoS can actually get around some of the security mechanisms that we actually put into place. They typically fall into two categories. Volumetric attacks, which is basically just trying to overwhelm some resource in our network, and then application level. So application level would be more like TCP send requests and just leaving half-open connections unattended. DNS is also a typical attack vector for DOS and DDoS, trying to overwhelm those services in our network to make them unavailable for normal use. It's important to note that in this whole CIA triangle of providing threat defense in our networks, that we include the notion of what's called non-repudiation. Integrity is actually provided for by way of hashing. Availability, again, gets into the robust nature of our appliances, etc. And then confidentiality is about obscuring the data in transit, right, and preventing it from being able to be read while in transit. So again, the way we get to this is by way of hashing. Hashing is, again, providing our integrity. Encryption, either symmetric or asymmetric key encryption, is scrambling the data so that if somebody captures the data, it's unreadable. So hashing is a function that basically takes clear text data, okay, so we have some clear text data, a password, some user-created packet flow of information, etc. And we run it through a one-way hash function. The one-way hash function basically takes this arbitrary amount of data, runs it through a one-way algorithm, and produces what's called a fingerprint or digest. If you've ever downloaded a piece of software, for example, from Cisco.com, they typically provide a fingerprint or a digest based on some hashing function to say, this is what the hash of that software should look like. And you can actually go into network devices and validate that what you downloaded hasn't been changed while in transit by simply doing a hash comparison of the data received based on the fingerprint of the data, based on what the website says you pulled down. Now, what's important to note about hashing algorithms is that a hashing algorithm is some of these, and what you're really looking at here is you're really looking at more of a timeline kind of coming across here. So we no longer really use, well, we do, but we no longer really want to use things like MD5 and SHA-1, primarily because vulnerabilities in those have been discovered and exploited. So the SHA-2 family of hashing algorithms is really what we're focused on. And I'll go ahead and say this now, the longer the digest or the fingerprint, which is what's represented in the 64, 96, and 128-bit hex are represented, the better. So longer is always better because it's harder to have what are called hash collisions, which is effectively inputting two different data sets and coming up with the same fingerprint. That's what's called a hash collision. Encryption, by contrast, provides our confidentiality, okay, and it provides it in a number of different ways. So at the application layer, pretty good privacy for encrypting email messages is one use case of confidentiality. At the session layer, SSL and TLS for encrypting website contents, etc., is used. At the IP layer, we have IPSec, and we'll talk in pretty good detail about IPSec. And then at the link layer, we have MACsec. And all of these, what these all really accomplish is this idea of scrambling the data in such a way that, again, somebody that intercepts the data can effectively not be able to read it without having the associated information that actually encrypted it. as an example of that, we have here a notion where we've got some original data, okay? We run that through an encryption engine and come up with what's called a ciphertext. But depending on whether or not we use a symmetric key or an asymmetric key is really unimportant from the concept that our data is actually obscured in transit. The difference here, though, is that when it gets to the other side and we run it back through the decryption engine, that we come up with the same original data. And so we'll talk about the ways that that some of the different mechanisms that we use to actually encrypt data are actually done. Now, with regard to that, encryption can either be what's called symmetric key, which basically, and again, what you're looking at here is more of a timeline related to the evolution of networks. But symmetric key basically means that we use the same key to encrypt and decrypt the data. Asymmetric encryption uses a pair of keys, usually a public and a private key, and sometimes also relies upon what's called a PKI architecture, or a public key infrastructure architecture, to actually implement the encryption of the data and the decryption of the data. And so again, what you're looking at here is you're really looking at a timeline, right, with regard to both symmetric key and asymmetric key encryption. Now, what's going to be important to note is the differences. We don't really use DES and triple DES as much anymore. Most of what we use now is AES encryption from a symmetric perspective, largely because it has higher security capabilities than DES and triple DES. Now, let's talk about some of the ways that we actually implement this. So IPSec, which kind of lives at the IP layer, okay? So this is kind of layer 3 of the OSI model, layer 2 of the TCP IP model. What IPSec is IPSec is a framework that effectively provides for confidentiality, again, the encryption of our data in transit, integrity, validating that no changes to the data actually took place while the data was in transit, authentication mechanisms to validate, are you who you say you are, and should I be talking to you, anti-replay protection, and we'll talk about how that works, and then key management. So it provides for all of the major things that we're looking for in terms of securing our networks and securing our data. And so let's take a look at each one of these kind of in sequence. Now, IPSec has two basic frameworks: authentication header, which is not used a lot anymore, primarily because it doesn't have the quite robustness that encapsulating security payload has. It doesn't encrypt the actual packet that we're transmitting. In ESP, which is IP protocol number 50, and is said to operate in either transport or tunnel mode, and we'll talk about the differences here. ESP is the most popular choice. Now, the difference here is that between these two frameworks is, what does IPSec do, right, with the data prior to actually transmitting it? And so in ESP, we use various symmetric encryption algorithms, okay? And the difference between transport and tunnel mode is that in transport mode, we actually don't protect the original IP header. The use case for that would be like a site-to-site VPN, where we need to actually protect, or we need to have the ability to use, multicast and broadcast messages. So that would be a use case for that. Tunnel mode protects the entire packet. Again, depending on how we're actually applying this in our network, usually tunnel mode is what we go with. Again, with confidentiality, what we're looking at here is we're looking at basically encrypting the data so that we have the original data We run that through some kind of an encryption algorithm that produces a ciphertext. We transport that across the network or across the internet or whatever the case might be and come up with our original data, okay, after de-encryption. Now, DES, triple DES, and AES, these are DES and triple DES. DES was actually developed by IBM. It uses a 56-bit key. It is a symmetric encryption algorithm, so which means that the same key that is used to encrypt the data is also used to decrypt the data. Triple DES was a development that came after DES, and what happens is the data is actually divided into 64-bit blocks, and each of those 64-bit blocks gets processed 3 times with 3 56-bit keys. So it's a vast improvement over DES, but it's still been deprecated by AES. So what AES, the key lengths are much longer, 128, 192, and 256-bit keys. These are all symmetric though. RSA and SEAL, so RSA is asymmetrical and uses 1024 and 2048-bit keys. And then SEAL, which stands for Software Optimized Encryption Algorithm, is actually a stream cipher that generates a 160-bit key, but it's also asymmetrical, meaning that the key that is used to lock the data is different than the key that is used to unlock the data. Now, IPSec also provides for data integrity. So data integrity is effectively this way of taking clear text data, running it through a hash algorithm. The difference here is that when it runs it through the hash algorithm, it actually also matches or associates with that hashing mechanism a key, okay? And so hashed message authentication codes validate that in transit, the data hasn't been changed from source to destination. IPSec also provides for origin authentication. And right, so you'll hear about terms like Internet Key Exchange version 1 and Internet Key Exchange version 2. Internet key exchanges are effectively mechanisms of developing partnerships between peering devices across an untrusted network, because that's typically what IPSec VPNs are used for, is they're used for data in transit between or across an untrusted network, such as the internet. Now, of course, one way of doing that is with pre-shared keys. RSA, anytime you see signatures, this is really referring to some kind of a public key infrastructure architecture, but you can also have what are called RSA encrypted nonces, or numbers used once. And so this is where peering devices would effectively generate a random number and then use their public key infrastructure certificate architecture to exchange those and come up with a shared secret value to use in the transmission of data from peer to peer. In addition, IPSec provides for anti-replay protection. So anti-replay protection basically just allows for the sender to sequence the packets coming across the wire, and for the receiver to basically use a sliding window to say, you know, packet 1 received, packet 2, etc. Because what happens is if the receiver actually gets a packet out of order, it actually is considered illegitimate or untrusted traffic, and it will actually drop that. So for example, in this context, if I get packet 1 after I've already received packet 4, packet 1 would effectively be dropped from the transmission. And then, of course, key management, right? So again, the ability to, using a public key infrastructure, either using Diffie-Hellman or elliptic curve Diffie-Hellman, to actually generate across, again, that untrusted space, the keying to actually be used, and occasionally rekeying the connection to keep the data secure.